Hello folks, this is tutorial number 8 in the playlist which deals with the buckling analysis using the 3D Experiences FEA solver, which incidentally is ABAQUS. So I refer to these as FEA transitioning videos, and it's intended for people who are either new in 3D experience or they're perhaps trying to transition from the ABAQUS CAE program to the 3D experiences version. The way I handle these particular transitioning videos is find examples that are done entirely in the ABAQUS CAE program and available on YouTube and replicate the steps to show you that the interface and the icons are not actually straightforward and they're not identical. They're not even close to what you see in the ABAQUS CAE program. The current problem is called the buckling of a short elliptical hollow section, and I'm going to use the Riks method. This particular problem is given by the geometry here. In fact, it's done in YouTube by this fellow YouTuber, professor in England, and it is an elliptical hollow section, as you can see, and one end of it is clamped and the other end is translated axially by 10 millimeter. Uh, Shell elements are used in order to do this problem, and what you see is what we're going to be doing. Now, the problem is the ends of the hollow section are controlled by some reference points, okay, as they're referred to in the ABAQUS CE program, and I coupled those reference points to the periphery of the tube at the two extreme ends, and by imposing restriction on those reference points, I basically control the motion. It is assumed to be the material is assumed to be elastic with steel, with those properties on the top, and the plasticity data is given below, and I'm going to be using it as shown. Now, uh, the coupling that I will use is going to be involving kinematic coupling. So basically, use the kinematic option. Uh, the length of the tube is 300 millimeters, and the cross section is given by this drawing that is uh, not drawn to scale. Okay, the surface that I will draw is going to be the outside surface. That's the basically the negative side of the shell elements, and then I'm going to extrude them inwards by the given dimension. This data is coming from a paper that's way up there, and we are doing the middle row of this. Now, as I mentioned, that the surface that I generate in the 3D experience is actually the bottom surface. That's why when it's extruded, actually the shell goes by that different distance of 4.22 millimeter inward. Now, I noticed that in this table, it says the thickness is 4.16 millimeter, but the fellow YouTuber where the reference is coming from is using actually 4.22. I'm not sure why he changed that. But anyway, let's move on. As I pointed out, they're going to be shell elements, reduced integration. The ends are kinematically coupled to reference points. This is the calculation is done by the Riks method, static Riks method with this data that you see here for the controlling the algorithm. And we will, because Riks method uses the arc length algorithm, we're going to specify a stopping criteria, which means that uh, that reference point is not going to be should not move more than 10 millimeter. Okay, so I'll use these values, and basically stopping criteria is based on the translation of that reference point. And there's one thing here, and that is the YouTuber is actually uh, his z-axis is along the tube. For me, the way I'm going to do that, it is the x-axis that's along the tube. Therefore, I will not use this 3. I'll change it to 1 because my x is along the length of the tube. Okay, so let's move on. We're going to obviously include the effect of nonlinearity, geometric nonlinearity. And this is the data that is taken from that paper. And the plot that you see in the top left corner is the force displacement curve of the YouTube reference. And this is the force displacement curve that I will be getting, hopefully, assuming that I don't make any mistakes. All right, so let's move on. Okay, here is the interface for 3D Experience. Because we're going to be creating a surface and mesh it with shell element, what I'm going to do is go to the generative shape design. There we are. And on that vertical plane, I will sketch. I want to draw an ellipse, so use the ellipse icon here. Here's the center of the ellipse, and then yeah, here's the center of the ellipse. And now for major and minor axis, what I can do is I can type in the values here. So major axis is 75, and the minor axis is 37.5. Half of the values that I gave, 150 millimeter and 75 millimeter, half of them are going to be these numbers. And there we are. So this is my ellipse. All right, we're going to exit that, and we're going to extrude this on the surface. We're going to extrude it by 300 millimeter. That was the length of the tube. Good. Let me hide this sketch, by the way. Hide that. Okay, good. Here is our ellipse. Why don't we apply our material? So let's go ahead. Let's go to the tools, and under create a material, I'll put down here short hollow section, SHS, right? December, what's that? Today, 28, 2023. We say OK, and wait for this thing to pop up in our database right here. So I'm going to apply to that part, and we put in our numbers. Okay, so let's go here, double click on that. So structural, it's ABAQUS multi-physics, mechanical, elasticity, elastic, and the value that was given in the slide, it was 217, 217,700, very close to properties of steel. So megapascal, 0.3. Okay, and then we go to plasticity, metal plasticity, plastic. Two values. The yield strength was given as let me see now, 373 megapascal, 373 megapascal at plastic strain of 0. That means yield strength. And this second point was given as 514 at 0.18 plastic strain. This data came from the paper and the YouTube reference. Okay, so I'm going to create also 2 points, one to the right, one to the left of these extreme ends. So let me go back to my generative shape design. So under essential, we create 1 point, and this point is going to be 100 millimeters to the left of this end, so it's going to be minus 100. Okay. All right, so the first one that I did is right here. This is the moving one, okay? And then another one on this side, which is going to be 300 plus 100. So that's going to be 400. 400. And we say OK. So notice that I've created 2 points here. This one, that's the fixed point. This is going to be the moving one. All right. It's a good idea to, if it's a good idea if I call these things, uh, this one is the moving one, this is the fixed one, but I'll just leave it the way it is. Okay, so we are pretty much done here. Now we're going to go to the structural model creation, MTFEM. All right, under the meshing tab, we'll use surface quad mesh of that surface. The size is, I think we agreed on what was used in that paper, in that YouTube reference was 10 millimeter, right? S4R 10 millimeter. Okay, so we go here, 10 millimeter. We say okay, it's gonna mesh it. I mean, we can look at the mesh, but if I update it, I will be able to see the mesh right there. And the property for properties, I'm going to go to properties, shell section, select that surface. Okay. Now 4.22 millimeters, but this surface that I created is the bottom surface of the shell. So we have to do that ourselves. We go under advanced tab, under offset definition from bottom surface. Okay. So that is, um, let me see for a second. It's right here. It's this slide. Okay. Now, incidentally, these colors mean something. The blue means it's the bottom surface of the shell, and the magenta is the top surface of the shell. But anyway, that's fine. This is good enough. We say okay. All right. While we are here, we create our connections. Connections. Where is that? Under. Let me get to connections. Let me get rid of this. Unpin it. Okay, connections. Here's the coupling. The first one is going to be between uh, this first one is going to coupling one is going to be the moving one. Okay, so for the support one, I select that edge, and for support two, I select that point. That's the moving point, right? And then we say that this is a kinematic coupling. Oops, where's that? Kinematic coupling, and all degrees of freedom are uh, checked. That means that the motion of this point determines the motion of all the nodes on this edge. We say okay, and then another one over here. So another coupling between this edge, and for the support two, I'm going to select this point. This is a fixed point, and kinematic once again, and all degrees of freedom are coupled. Good. Now, if I update here, I will see the entire coupling here shown. Good. That's pretty much it. So let me do a quick save here. And now we're going to go to the structural scenario creation. Remember, the finite element is done either here or there. This has uh, certain features that the one that we're using does not have. For example, if you want to do explicit dynamics, you have to go to this guy, to mechanical scenario creation. But we are doing a Riks step, so we go to structural scenario creation. Okay, we are doing structural, and the finite element mesh is the one that we created. The one thing I forgot to do, and I'm going to do that right now. Once I create, you will see, once I create, I'm going to define the type of the element. First of all, there's no procedures described here, so I'll go in the procedures tab, and I'm going to do a Riks step, right? Riks step. And the numbers are going to follow what I gave you here for controlling the Riks, okay? So let's see now, 0.01, these are arc length information, 0.01, okay, so let's go here, 1000, 0.01 is the initial arc length. This is going to stay the same, maximum arc length, also 0.01. And under stopping criteria, maximum displacement, translation, and the degree of freedom to stop is degree of freedom maximum is 10 millimeter. Now this is what I was saying. You have to be careful in the YouTube video. I think the way the gentleman did it was his was 3, but mine is 1. This is the one direction. Okay, and the node is that node where it's moving. Okay, and the value is 10 millimeters. I don't have to check because this is already done by default. The default include geometric nonlinearity is included. So that's okay. So we got everything that we need here. You say okay. So I just took care of that guy. Okay. And now we're going to go and apply the boundary condition. Now, before I do that, let me point you, as soon as I did the procedure, element type appeared here. I double click on it. And I don't want S4, I want S4R. Say okay. Reduce integration. All right, so let's go and apply uh, our boundary conditions. Boundary conditions, I'm going to get rid of this, get rid of these things so that I have only basic stuff that I want here. Okay, so there we are, boundary condition. And this is going to be the clamped end. So let's start with this, clamped end. I'm not going to use clamp because the icon, I don't like it. So I'm going to use, instead of clamp, I'm going to say fixed displacement. So on this point, all 3 degrees of freedom are fixed. Okay. So this is going to be, I'll call it fixed. How about calling this thing clamped? Clamped end. Clamped end. All right, good. And this one is allowed to move in this direction. So fixed displacement here at that point, I'll call it moving point, moving or translating point, translating end. Okay, so it's free to move in direction X, but Y, Z, and rotations are fixed. Good. And now we say that this can also apply translation on that same point. See that? Same point in the direction X by 10 millimeter. Oops, what is that? 10 millimeters. And we say, okay. We can see that there is an arrow right there, which represents the translation. Okay. That's pretty much it. I don't think we have forgotten anything. Yep, so let me save this and go ahead and run it. All right, so we go to the simulate. Let's do a quick model check. I think it looks good. Simulation check. If there are any obvious errors that we have made, it's going to pop up here, hopefully. I don't anticipate an issue. Okay, that's pretty, it's done. When that, okay, there we are. Close that. And then we simulate. Say okay. This is the running stage. And if you click on the iteration tab, you're going to get the equivalent of the monitor tab in ABAQUS CAE. It's going to be fairly fast. Yep, we're almost at 1. 1 is when the time step ends, the dummy time step ends. Yeah, extracting results. Say okay. All right, so that is the, if you look at the displacement, this is the initial step. And as I make this thing bigger and bigger, the different stages of deformation are going to pop up. You can see that. Okay. So I just noticed that, see, uh, this is the displacement. Of course, this is the end that's moving. If you look at the stress, you're going to get something like that. And this mode of deformation, okay, uh, actually agrees with the experimental modes of deformation. Now, we're going to generate this plot here. Incidentally, if you want to see your elements, you click on this thing, and on the last tab here, you say, show me the mesh if you want to see it, and then say, okay. You can see the mesh. Anyway, this is fine. Now we're going to generate the plot that I want. So what we do is we go here under plots, and you click on XY plot from field. So we don't, we want for example, what is that? Template, the template under displacement template. See that? Displacement template. And I want the translation of a point. Now the point, I can get it from, for example, from here. Hang in there. From the actually, let's go here. Hang in there. Select the node. We can do node set, and from the node set we can do coupling 1. Remember, coupling 1 was that node on this side, that point on this side, coupling 1. Okay, very good. And what do you want? The magnitude of it. Magnitude of the displacement, translation. You say, fine. Okay. And then another one, let me close that. Another one, XY plot from field. This one is going to be, once again, the node set, coupling 1. Yeah, that was this end. And this is going to be, the template is going to be reaction forces. And from there, I use the CF. Let's see now. We can do well, this should be, let me use this thing coupling 2. That's this end, okay, the fixed end. And reaction force. Okay, reaction force magnitude. Good. Now, both of these are plotted against the arc length. I want displacement against force, or force against displacement. So we say, fine, we generated these two plots here. You can see that in the results of generated the two plots, and I can look at any one of them if I wanted to. For example, let me deactivate this, and this first one is displacement. Notice that it's against arc length. I don't want displacement against the arc length. What I want to do is plot this force versus displacement. Let me deactivate this. So I go here on the XY plot from expression, and click on f of x. Click on combine. For combine the displacement on the horizontal axis and force on the vertical axis, and then we say okay. There, this is that plot. Okay, and they agree pretty much. So that takes care of this video tutorial. And as I said, the purpose of these this particular playlist and these tutorials that I'm making of the experience is give the ABAQUS users the opportunity to be able to do things on 3D experience should they wish to do that, but you can see that it's completely different as far as the interface and the icon sequence of things, dialog boxes, etc. I hope you found this thing useful. There will be another video of the same YouTuber where I do a long section, but the cross section is going to be square, and also there is the end condition is actually the same.